You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you.
Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast. I have two guests today, Michael O'Neill. He's the media lead, and Laura Potterat. She's the avionics lead. They're at the USC Rocket Propulsion Laboratory. The acronym is USC RPL. It was founded in 2005 with the goal of putting a student-designed and built rocket into space. So, guys, thanks for coming.
Thanks so much for having us.
Yeah, thank you.
So the goal is to put a student-designed rocket into space, but what is some detail around that? Is it just a rocket that's going to carry a payload? Is it just a rocket that will get into space, period?
Yeah, so back in 2005 when the lab was founded, no other student group had made a rocket that actually had gone that high. So in terms of classifying what space is, our metric is what's called the Kàrmán line, which is kind of an internationally agreed upon line that's 100 kilometers above the surface of the Earth, which is about 330,000 feet. And so we set out to initially just to get a rocket that would go that high and come right back down. And then getting into taking a payload or anything further would kind of be next step. So it was created, the goal, just to get up there and recover the rocket successfully when it came back down.
What part of the atmosphere is that called at that height? Is it still part of the atmosphere, or is it the mesosphere, or what is it called? Yeah,
I'm not actually sure. Lauren could probably speak better.
As far as where in the atmosphere goes, the way that we typically categorize it is just by saying, aerodynamically speaking, it is at an altitude where we can no longer sustain winged flight. So theoretically, you cannot fly a plane past the Kàrmán line. There is no hard demarcation, so it's not this exact demarcation line between the mesosphere and the stratosphere. But effectively, you can no longer maintain winged flight. It becomes much more of an aerodynamic problem for rocketry than it would be for typical aerospace.
Why can't you maintain winged flight? Like, what is it? Is the air just? Is there mostly vacuum? Is the air very thin where it won't sustain? You can't create lift. Like what? Like why?
Yeah, exactly.
Okay, so the air is too thin by that point. How would you compare it to the the air at surface level? Like how depleted is it? How much of it is what's the concentration?
I honestly, off the top of my head, would not know the answer to that.
Okay, well, that's all right. Well, what becomes important at that point? So you have a rocket that gets to that height. Your goal is to go beyond that height?
Right. So like Michael said, our goal is to be the first undergraduate student organization that entirely built from test and development to actual production, the first rocket to go to space. And that was it was something that had never been done before at the time, back when the lab was founded, and really hadn't been accomplished until we did it this past year. So it was kind of this novelty of, okay, well, has once been the task of nations. Historically speaking, it would be governments pooling resources together in order to obtain this goal. And we thought, all right, well, we're a group of scrappy engineers at the undergraduate level, but it's always felt so close. So through the entirety of lab history, it's always felt as though that generation can do it. And we just happen to be the group that then pushed this like nearly 15-year development project over the finish line. And now, like Michael mentioned, it's about providing reliable access to space. So doing what we did, but again, and better and more reliably.
Well, how much more is there to go once you got into the Kàrmán limit? Are you quote unquote in space, or are you still in the atmosphere? Like, how much further is there to go?
Right. So technically, we're in space past the Kàrmán line. So that was the initial goal. There's several reasons that we can't go very much further, primarily because launching into orbit is a whole other ballgame that we aren't really looking into at this point, just as far as the development and the engineering that would take. So for us, it was reaching the Kàrmán line. And at our level, as far as what's next and what could this mean, so we are in space at this point, so let's do it again. But things like deploying small satellites or CubeSat programs, or just kind of getting our feet wet with what going into industry rocketry would look like by releasing these payloads then in microgravity to see what data they could obtain then at a microgravity level. But we're not putting anything into orbit, just to clarify.
What's so different about putting something into orbit, even like a low Earth orbit? How much more effort is required, and what's different about that?
Right. So I mean, just purely as far as the sheer distance goes, we reached 100 kilometers, like Michael said. So 100 kilometers is the Kàrmán line, and that's where we're near vacuum, so it's considered to be space. LEO, so lower Earth orbit, is actually about 2,000 kilometers. So we're on a whole different order of magnitude as far as the engineering ability and getting there.
Oh, I didn't realize there was such a big difference.
And as well, another thing I'll point out too is getting to the height and distance above Earth is one thing, but then getting enough actual horizontal speed to sustain orbit is another. So currently the technology we use is single stage solid rockets, which doesn't allow for any control of like the throttling of the rocket itself. So it's essentially once it's going, it's going to burn to its fullest extent, and there's no way that we can control or position it. And so actually getting that vertical height to get high enough to orbit, and then having the horizontal speed to actually go around the Earth, being able to control to get that horizontal speed is very difficult with just the type of rocket technology that we're using.
Because of the rotation of the Earth, what's the rocket's path look like? Does it just go straight up, or does it start curving and bending over in the direction of the rotation of the Earth?
It for the most part goes straight up and comes back down. There's a bit of an arc, and depending on wind conditions and a few other things, it'll land at a different spot. But we have a simulations team which before the launch takes into account the weather conditions and the position that we are launching from, and so they'll do all these calculations and all these simulations minutes before launch to give us the exact correct placement and pointing of the rocket, so that we can launch it and hopefully get it back as close to launch site as we can, so that we can recover it afterwards.
Is your goal simply to just go higher from here, or like what's your goal now that you've reached this height?
Yeah, so I think Michael, do you want to go? Or?
Sure. I think once we made it to that Kàrmán line and really did achieve the lab's initial goal, that does open up kind of a number of possibilities for us to go into. So the first, I will say, like Laura mentioned earlier, is the possibility of CubeSats and actually having a useful payload being put up in the rocket. So that would allow other, maybe even student organizations or other people who want to do some research and get data from that high up out of the atmosphere. That would make that possible at a much kind of cheaper and much easier level than what's currently available. So that's one thing that we're definitely looking to get to next.
How could you deploy any CubeSats? Wouldn't they just fall right back down to Earth?
Well, at that point, they would linger in microgravity. So they would fall eventually or disintegrate. But you would have a good, minute-ish to collect data. And also adding on to the, what's next. Because it brings up a good point, right? If the entire lab was founded on the basis that we were going to reach space, once you do that, what's next? So So despite the fact that we did reach space and have confirmation to do so, that doesn't necessarily mean that we went without several technical challenges, and that we can see places within different subteams in which we could improve designs. So it's more of like leading into next steps. I know specifically I can speak on the avionics side, as so Michael mentioned, that if we ever kind of escalated to implementing a control system or something similar, we would need to start that experimentation relatively soon. So kind of dealing with the fact that perhaps we would integrate something like that, starting to get some real-time controls on board within the flight computer, and also dealing with just basic telemetry issues. So communication to rockets is very, very difficult, and we've seen that ourselves, and are basically always refining and trying to come up with new, creative, scrappy ways that we can talk to the rocket when it is going incredibly quickly and to an incredibly high altitude. So a lot of our issues are kind of looking at the data that we obtained from our past flight of Traveler 4, which was the space shot, and saying, okay, well, based on how this worked, how can we do this better the next time? So we actually experienced pretty significant roll off the pad. So the rocket spun pretty hard. We were about 60 hertz. And that converting like that much energy and roll, eventually it will detract from our overall altitude projection. So the simulation said that we would actually reach a higher altitude than we did, but because of the loss of kinetic energy upon rolling, we didn't reach that. We still reached space, so that was the initial goal, and that was fine, but we lost some of that margin. So knowing that we designed the vehicle to actually...
One second. What do you mean roll? You mean when the rocket launches, does the pad it sits on move, or does the rocket launch
the actual rocket body starts to spin rather violently, and this could be through a series of factors. So we actually hand make the entirety of the rocket. We kind of joke and say it's artisanal. So even small deformations can result in this roll off the pad, and that will detract from the overall altitude of the final flight. And so knowing these things and kind of going back and looking at our designs in sort of a post-process allows us to then take the next step of, okay, so how that we've done this now, we've done it once, but we can do so much better. And I think that that's a lot of what's driving Lab currently. And I at least I know from an avionics side that that's a lot of what we're focusing on.
Is it wobbling and spinning, or just spinning?
Both. I mean, so I'm not sure if you've seen the video. There is a cool video, but it does a bit of a wobble and a spin. So the spin is fairly normal. To have it spin as fast as it did is not, based on simulated data that we had. And that's, again, just up to several deformations within the case, or perhaps the way the propellant was burning, and it's a whole variety of factors. So it provides really good experience with students, because this is something that you would see in industry as well. Like, okay, post this flight, here's our data, here's what happened. How can we then reflect on this and iterate forward? And Rocket Lab primarily is this like learning laboratory, right? So as much as it'd be nice to function similar to a company, our goal is to kind of learn from our past process to achieve the future process. And because of this iterative development, we're able to kind of push forward the next generation of undergraduate rocketry.
Why not design in elements to make the rocket spin one way, and then design in other elements on the other side of it to make it spin the opposite way to keep it stable and stop spinning?
Yeah, so the rocketry technology that we use as far as stability goes, because we are a solid body, we use, historically it's always been a passive stabilization system. So the fins on the very bottom act very much like a dart, in that they passively stabilize that rocket, which doesn't mean that it ideally isn't going to roll, but it keeps the rocket from doing like a death spiral, effectively. So after years of trial and error, I believe we went from we attempted a 3-fin rocket, and we have stuck with 4 since then, for stability reasons. But as far as what you're talking about, like roll control, that kind of gets into this new area of active controls, which is something that we haven't dealt with at all, and it's something that avionics is actually looking into right now. So my team is avionics, which means aviation electronics, and we basically focus on the brains of the rocket. So the flight computer, how it knows when to deploy recovery, collecting data, transmitting data. And our next step then, like our next big leap, is, okay, well, how do we optimize our trajectory? Which is exactly what you're talking about. Like, oh, hey, we're rolling too hard. Maybe we should roll the other way, or do something to counteract that. And there are a variety of mechanisms in which we could do that. But a lot of that stems from the core of, okay, we need to build a more robust flight computer. It's kind of taking these baby steps to get there, but definitely. So we could implement, like, cold gas thrusters are a pretty common way of combating roll off the pad. So kind of putting different valve features outside to spin and counteract any roll that we'd see. But it's a lot of built-in infrastructure that we're experimenting with currently.
Okay. So what is the fuel that you guys are using? What kind of engine?
What kind of?
Yeah.
And so, okay, Michael, you go.
Sure. So as I mentioned earlier, the type of rockets that we use is single stage solid rockets. So the keyword there for fuel is solid. So to contrast, the other main type of rockets that are out there in industry now are liquid fuel rockets. And so the main difference is that in a liquid fuel rocket, you have big tanks of like liquid oxygen and things like that that you can pump with different valves and pipes into a combustion chamber that then will ignite and produce the thrust for the rocket. So as I mentioned, there's a lot more moving parts that go into that. And so when the lab was created, we decided to really focus on solids. So basically the process of it, like everything else in lab, we completely do all of it ourselves and make our own rocket fuel. So we have essentially it's a recipe, so to speak, of different chemicals that make up the solid fuel that go in the rocket. It's quite similar to what was used on like NASA's space shuttle on the solid rocket boosters, and essentially it comes out in like a kind of a pencil eraser type consistency that is packed into a very specific shape that burns at a predetermined rate that can be simulated, and so that is then put inside the rocket and ignited when we're ready to go. And the burn rate just kind of it just burns up the whole remainder of the fuel, and there's no real control systems on it.
Yeah, how do you control the burn rate? And would it be best, like, what would be the ideal way for it to burn all up at once, so you have the lightest weight and then all the thrust initially, or like a controlled burn rate?
Mm-hmm. So the burn rate actually depends on the geometry of the hole that's in the center of the fuel. So if you imagine it's what's called a grain, it's basically a cylinder of this rocket fuel with a hole in the middle. And so currently we use just another smaller cylinder right through the middle, and that's what ignites, and then basically the fire burns inside outwards towards the edges. And so there's different ways that you can design these geometries so that your overall burn profile looks different throughout your flight. So one thing to think about is when you're lower down in the atmosphere, there's a lot more air molecules and a lot more air friction that builds up a lot more heat. So if you can have a little bit less thrust down in the lower atmosphere, and then once you get higher up where there's less air friction and less heat buildup when you start going fast, and then the thrust actually starts to increase, that's something that could increase performance and decrease kind of the wear and tear on the outside of the rocket.
I guess you want it to burn as fast and efficiently as you can without making it explode, right?
Yeah, well, I think there's definitely a balance, and like I say, it's important to consider the different altitudes at which you're going to be getting these different thrust profiles. So to have a really high level of thrust right off the pad in the lower atmosphere is quite taxing on the outside of the rocket when there's so much air friction. So trying to mitigate that and make a bit more of a increasing thrust profile as the rocket accelerates upwards and gets higher is definitely kind of the goal.
Oh, okay. But then you're carrying more weight for a longer period, so it's a funny trade-off, I guess.
Right.
That's interesting. Huh. So you want the thrust to increase as the atmosphere is thinner, and you can move through it with less resistance. Makes sense. Interesting. What about the what other factors were really important to make this work? What other difficulties did you guys run into?
I mean, the whole. So yeah, Lauren, you can go for this one.
Yeah. So a lot of the difficulty with our rocket's performance was actually characterizing that performance. So we can launch this rocket, but we need some way of communicating with it to understand where it is. And a lot of that turns into a big computational problem on our end. So as far as building the flight computer goes, we need to kind of comprise this customized sensor suite such that we are able to obtain critical data. So, acceleration, hopefully position. Effectively, we want to characterize critical data. So our rocketry position, velocity, acceleration, and then seeing how, once we obtain that, how do we transmit it to ground so we are aware of what the rocket is doing at any given time. And then, especially given the goal was, an absolute altitude, we want a way of determining that altitude. A lot of the trials we went through is there was no way that we could really test our sensor suite besides flying it. So we don't have a simulated environment where we're going Mach 5 and at an 100-kilometer altitude. So a lot of the redundancies that we built in from the software side and the hardware side were based on previous years of trial and error from previous flights, some industry knowledge, and then really just kind of keying in on making the system as fault tolerant as possible, which is super cool because now the recovery actually of Traveler 4, we obtain the avionics in one unit back. And so now we have on our avionics bench sitting in lab, we have the actual flight computer from that vehicle, and we can be like, this made it to space and back. But one of the biggest trials and tribulations always is the actual brain of the rocket. So making sure that we are communicating to it and maintaining that data link is something that we always kind of bite our nails with.
Okay. And Mike, go ahead. Any challenges from your side that you saw or worked on?
I think as I'll speak of the lab as a whole, and just kind of getting to this point where we are today from 15 years ago. It's definitely a tricky situation being an undergraduate group because we lose our top 25% and our most experienced members every year when they graduate. So compared to something like in industry and these big companies where they have engineers that are working there for long periods of time, we really have to focus on passing down knowledge from person to person and class to class, as like I said, 25% of our most experienced engineers graduate each year. So I think coming up on about 15 years of being a lab, it's incredible how much of a system that we've developed with passing along information and making standard operating procedures for everything that we do when it comes to constructing the rocket. And so it's really cool to see it all come together and finally have a successful space shot rocket with so many years of research and development being able to be passed down to a lab that is essentially completely different and all new people than it was 15 years ago.
Oh, so you in the phase where you're documenting and procedurizing stuff now to for when you guys are no longer working on the project, or what are your particular roles as of this moment?
Exactly. So everything that is done in lab from how the case itself is made to how the launch operational procedures go, how materials are ordered from our various suppliers, everything we document very well because we know that when we're gone, for Lauren next year and for me in 3 more years, but once we're all gone and there's a new set of students and members, they're going to have to rely on the information that we've written down and passed on to them. So everything that we do, it's important to record and document. We actually have our own internal wiki where each subsystem, each rocket has its own page, and everything that could be useful to people in the future, members of lab in the future, is documented there.
Okay, gotcha. So what's the timeline you think where you'll be looking at CubeSats and other additions to the rocket itself?
Yeah, so as far as like next steps for launch, so we're actually going to be flying a hopefully the sophomore design vehicle, which is a smaller scale vehicle. It's actually upcoming in a few weeks here, ideally, and it acts as a proof of concept. It's not designed to go to space, but it's flying various different set of kind of miniature experiments for each subsystem of what if we change this parameter to kind of see how that would scale for a space shot. And we are actually in the design and development phase for our next space shot vehicle, which I was mentioning as far as like iterative development is going. So on an avionics side, the actual unit, so our flight computers are getting a complete rehaul, looking completely different, basically tuned into the fact that we saw the difficulties and the challenges that came out of the past flight and seeing how we can iterate forward. So how can we make the flight computer better? based on what we saw in the data we obtained from the previous flight. So going into the next space shot, I know a lot of parameters are being changed, and it's effectively focusing on this reliable access to space, so then we can start entertaining the idea of introducing things like CubeSats. But first, we want to obtain that reliable access.
Okay, well, very good. So, what's the timeline from here? What do you think is going to happen over the next 6 months or a year?
Yeah, so we'll be launching sophomore design vehicle definitely within the next 6 months. Ideally, that's upcoming here in a few weeks. And then within the next 6 months to a year, we're going to perform another space shot, so very similar to Traveler 4. And then from there, it's really seeing how that rocket goes that then pushes the next set of iterative development forward.
Okay, well, very good. So what's the best way for people to find out more, maybe see pictures or videos of what you guys have done, or read about it? Where can they go?
Yeah, so we have a website, uscrpl.com, and there's pages for most of our rockets in the past that we've done. There's actually a page of Traveler 4, which was our successful space rocket, and it has a whole basically overview of the rocket itself, kind of an inside view and descriptions of all the different systems. We also have a YouTube page with videos from inside lab, and we were actually lucky enough to have a film student from USC document our progress over the past basically year or year and a half. So everything from last year, our previous space shot attempt, Traveler 3, and the whole build process of Traveler 4 and the launch of Traveler 4. So he actually made about a 30-minute documentary called Space or Nothing, which you can find on Vimeo.
Oh, well, very cool. Well, Mike, Lauren, both of you guys, thanks for coming. I really appreciate the call.
Yeah, thank you so much.
Thank you very much for having us.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.